In this video, we're going to talk about the comparison tests. So in the last section, in the integral tests section, we saw that both the series 1 over n squared and the series 1 over 1 plus n squared are convergent series. The first one here is a p series with p equal to 2, and this one, when we did the integral test on it, we got inverse tangent for our antiderivative, which of course, if you do the improper integral, it converged because we had that limit of inverse tangent as x goes to infinity. So both of those series converge, and again, obviously, at least maybe not obviously, but I don't think it's horribly surprising that both of these things did this. Both of these series did the same thing. They both converged, because if you look at the denominator in both of these series, as n gets really, really big, there's not a lot of difference between dividing by, say, 1,000,000 versus 1,000,001. These terms are essentially the same when n gets large. They both look like n squared as far as the denominator goes. So it makes sense that they both should behave in a similar fashion. So that's exactly our point of the comparison tests. If we have similar series, at least similar terms in series, then the two series themselves should behave in the same way. So we're going to have two comparison tests to help us out with determining whether or not series converge or diverge. And for both of these tests, we're going to assume that our series have positive terms. All right, so the first one is what's referred to as the direct comparison test. So it says, suppose that our terms for our a sub n series are all less than or equal to the terms for our b sub n series. The first conclusion is that if the series of the b sub n's converge, then so do the a sub n's, the series of the a sub n's. This makes sense, right? Because this is kind of the same idea with the integral test. This is bigger. When we add all of these things together, that should be bigger than adding all these things together. So if this one turns out to be a finite number, then this one also should turn out to be a finite number. Going the other direction, if the series of the a sub n's diverges, then the series of the b sub n's should also diverge. And again, that makes sense if you think about it. And again, it's kind of the same integral test argument. If this sum goes off to infinity, and these terms are bigger, then this series should also go off to infinity when you start adding those things together. So that's the direct comparison test. We also have what's referred to as the limit comparison test, and this is really more along the lines of if they really do have similar terms, then the series should behave similarly. So that idea of having similar terms is what this condition is here. Suppose that the limit as n goes to infinity of the ratio of a sub n to b sub n exists. Suppose that limit exists, so that's what the less than infinity part is, that it actually exists as a number and it's not 0. So meaning what this means is as n goes to infinity, a sub n and b sub n have similar terms. The ratio settles down to be some value in terms of a limit. So then that says that what one series does, the other does. So it says the series of the a sub n converges if and only if the series of the b sub n converges. All right, so when we're using the comparison tests, we have to have something to compare the series to. So there's two classes of series that we know by looking at them whether or not they converge, and those are the p series and geometric series. We already mentioned that up here when I said that this series, the 1 over n squared series, converged because it was a p series. The p was equal to 2. So again, by looking at a p series, I can tell whether or not it converges just by looking at what the form of the terms. The same thing is true for a geometric series because I just need to know what that ratio is, that r is in the r to the n piece. That gives me a nice condition of whether or not it converges. All right, so let's go back to the series of the 1 over 1 plus n squared and show that this converges. We've already done that with the integral test, but we're going to use the direct comparison test on this one, just to give an example of that. When we're using these comparison tests, we have to know what series are we comparing it to. Now, in the previous slide, we already mentioned that the 1 over n 1 over 1 plus n squared looks a lot like 1 over n squared. So that's what we're going to compare it to, is the series of 1 over n squared. In order to be able to use the direct comparison test or the limit comparison test, we have to have series that are all positive terms. We should make note of that, but if you're using the comparison test, most likely you already have that by just looking at it. All right. So if we're going to use the direct comparison test, I need to show, and we know that this one converges, it's the convergent p-series. I need these terms, the 1 over n squared, to be bigger than these terms, the 1 over 1 plus n squared. That's not that hard of an argument to make. Well, certainly n squared is less than or equal to n squared plus 1. In fact, it's strictly less than. And then if we take the reciprocal of both sides, well, when we reciprocate, the inequality flips. So 1 over n squared is greater than or equal to 1 over n squared plus 1, and this is true for any n that we want. So we already mentioned that the series of 1 over n squareds converge, and the terms of the 1 over n squared series are bigger than the terms of the 1 over 1 plus n squared series. So that tells us that the sum of 1 over 1 plus n squared converges by the direct comparison test. The series, again, what we're saying here is the series with the bigger terms converged, so the series with the smaller terms has to converge. Let's do another example using the direct comparison test. Let's look at the series of 4 plus sine of n over the cube root of n minus 1. When we don't specify an index here, or we just have the sum and not specify an index, we assume that the values for n have to start somewhere that are in the domain of the terms. Right? I don't want to plug in 1 in particular for n here, so this series must start at 2. And there's nothing wrong with it starting at 2 or 7 or 15 or whatever. All of our tests, just like our integral test, both of these tests, as long as it's true at some point for the direct comparison test, as long as one term dominates the other term at some point onward, we're okay. We don't have to start at 1. All right, so let's do a direct comparison test. To figure out what we want to compare to, let's analyze these terms here. Well, the denominator looks a lot like cube root of n as n gets large. The minus 1 isn't going to do a lot. Well, we know that the series 1 over cube root of n diverges. That's a p-series. It's 1 over n to the 1/3. So I need to look, I'm assuming that this is going to be the bigger, this one that we're trying to determine whether or not it converges or diverges. That one's going to be the bigger series. Okay, so I need this one to be smaller. So if I look at 4 plus sine of n, the smallest 4 plus sine of n can get is 3, because the smallest that sine of n can get is negative 1. So that's why we're going to compare to 3 over the cube root of n. The cube root of n comes from the fact that this looks like cube root of n as n gets large. I know that that series diverges, so this one has to be the smaller series. The other one, the one we're trying to find something out about, has to be the bigger one if we suspect that it diverges. So that's why I used the sine of n being greater than or equal to negative 1. All right, so let's do this. Let's show that we really do have the 3 over cube root of n is actually less than the 4 plus sine n over cube root of n minus 1. Let's start with an obvious statement. Certainly cube root of n is at least as big as cube root of n minus 1. Reciprocating flips the inequality. Multiply both sides by 3. Inequality stays the same because we're multiplying by a positive number. This now is the terms of the series that we're comparing to. On the right-hand side, I'm going to replace with 3 with 4 plus sine n, and I know that it doesn't get any smaller. It can only possibly get bigger, so the inequality stays the same direction. And now we're just a matter of doing the conclusion. The series 3 over cube root of n diverges. It's a p-series. Actually, it's a constant multiple of the p-series. It's 3 times one of them. But the p is 1/3, which is less than 1, so it means that series diverges. And since this series has bigger terms, that series must also diverge by the direct comparison test. All right, we've had a couple of examples with direct comparison tests. Let's look at limit comparison tests. Let's see if this series of 5n squared plus 3n plus 1 over 9n cubed plus 7n minus 1 converges or diverges. It's a little harder to use the direct comparison test on this one because I don't have a real good handle on what's going on, especially with the minus 1 and all of these other things. So it's a lot easier to compare this to something that we know converges or diverges, but do a limit instead so that we don't have to worry about which way the inequalities go at any given point. All right, so let's look at this. And when we're trying to figure out what to compare to, just like before, we want to try to figure out what's going on as n gets big. Well, as n gets big, the top is dominated by n squared, and the bottom is dominated by n cubed. So that's exactly what we're going to compare this to. We're going to compare it to the series n squared over n cubed, which of course simplifies to 1 over n. And again, I chose 1 over n because that came from simplifying n squared over n cubed, which are the dominant terms in the numerator and the denominator. All right, so we know that both of these have all positive terms. It's important to make sure that you meet the hypotheses of a series test before you apply the test. The limit comparison test says do the limit of the ratio of the terms. Okay, so we're taking the 5n squared plus 3n plus 1 over the 9n cubed plus 7n minus 1 and dividing it by 1 over n. I want to take this limit. The way I typically do it is I rewrite my fraction here as what I use to figure out what to compare it to. In particular, we got 1 over n from the fact that we're looking at n squared over n cubed. You don't have to do it this way. You could just go ahead and simplify and then recognize what the limit is. I'm just doing this because I'm reiterating why we used 1 over n. It's because it came from n squared over n cubed. To evaluate this limit, let's put the pieces together that match. We had 5n squared plus 3n plus 1 over n squared. Those pieces kind of match. And then the second one we have, when we invert and multiply, we would have an n cubed on top over 9n cubed plus 7n minus 1. Now again, you could do some simplifying here and doing some work, but it's important to note that we can evaluate these limits kind of by looking. This is essentially 5n squared over n squared, so this limit's going to be 5. This is essentially n cubed over 9n cubed. This is going to be 1/9. So we're going to get 5 times 1/9 for our limit, or 5/9. Now we're ready for the conclusion. The series that we're comparing to, the 1 over n, is the harmonic series, so that diverges. So the original series must also diverge by the by the limit comparison test. Let's do another one. Let's look at the series n squared plus 7 to the n over n plus 10 to the n and determine whether or not it converges or diverges. So again, to figure out what to compare it to, we're probably going to compare it to a p-series or a geometric series, because again, those are the ones that we know what the convergence or divergence does just by looking at them. Well, here we're looking at n squared plus 7 to the n on top. Well, 7 to the n goes to infinity faster than n squared does. 7 to the n is going to dominate. Similarly, in the bottom, 10 to the n is going to dominate. So we're going to use the limit comparison test with the series of 7/10 to the n, because that's our dominant terms on top and bottom, the 7 to the n and the 10 to the n. Again, clearly both series have positive terms, so let's do our limit comparison test. Ratio of our terms, one series to the other. It doesn't matter which one goes on top and which one goes on bottom, by the way, because we need the limit turn out to be non-zero and not go off to infinity. So there's not a lot of difference between getting a limit of, say, 2 and a limit of 1/2. That gives you the same conclusion. So the order doesn't matter in which you divide these. All right, so this is going to put a 7 to the n in the denominator and a 10 to the n in the denominator down here. So this is going to be, if we think about rewriting this, I'll have a 7 to the n in the denominator on the top and a 10 to the n in the denominator on the bottom. Distribute that through, we'll get an n squared over 7 to the n plus 1 on top, n over 10 to the n plus 1 on bottom. We just mentioned that 7 to the n gets bigger faster than n squared does and than n does, so that each of these limits are going to be 0, so the limit of the whole thing will be 1. We know that the series 7/10 to the n converges because it's a geometric series with a ratio of 7/10. So since that series converged and the limit turned out to be non-zero and existed, the series that we're looking at also converges.